And this is what the tank looked like. And Ray's idea was that as trillions upon trillions of neutrinos stream through this tank, very, very occasionally, a few times a week, one would hit a chlorine atom. And it would turn that chlorine atom into an argon atom, a radioactive isotope of an argon atom. And by using charcoal and helium and other techniques, he said, I think I can count those argon atoms in this tank every month. And we're talking about 6 or 7 or 8 argon atoms a week in this 100,000-gallon tank, which was an amazing feat. That's Ray, by the way, standing up there in this tank. So he installed it, but there was a problem. This is John Mccoll, who was a famous theoretical physicist from the Institute for Advanced Studies at Princeton. And John Mccoll and other physicists had what they call the solar model, which basically described how they thought the sun worked and how many neutrinos it should produce. And John Mccoll predicted, and I'm going to get the exact, these numbers won't be exact, but it was on the order of 8 or 9 neutrinos would hit Ray's tank every week. And Ray fired up the tank and started running it, and he was only getting about 3 neutrinos a week. He was getting about a third as many as John Mccoll predicted. And of course, the first reaction to this was, your experiment has to be wrong. First of all, it would take just a tiny, tiny error in your measurements to miss a few argon atoms a month in this gigantic tank. But Ray Davis was persistent, and he kept at it. There were some mistakes in his experiment. He kept refining. It actually ran for decades, nearly 30 years. And turns out, research in Canada in the 1990s proved that Ray Davis was actually right. What was happening was neutrinos produced in the sun were changing type. And Ray was only measuring one type. The sun only produces one of the 3 kinds of neutrinos, an electron neutrino. There's 2 other types. Well, somewhere between the sun and the earth, neutrinos were changing flavor or type into the 2 other kinds of neutrinos, and that's why he was only detecting a third. And this sounds like a small thing. It was a huge thing in physics. It required a pretty serious rewrite of the standard model about how the universe works. And Ray was awarded a Nobel Prize in Physics in 2002 for his work at Homestake. So Homestake was famous already among astrophysicists. This picture appears in a lot of astrophysics textbooks. So along comes the other September 11th, which in lead is September 11th, 2000, and that's the day that Homestake Mining Company announced that it would close. And I went up to Leeds, and I had to write a story about that, and it was a heart-wrenching week in Leeds. My family history goes back to Homestake to the 1890s, as Keith said, and a lot of family and friends worked there over the years, and actually we're still working there at the time of closure. So the town of Leeds was devastated, but within 2 weeks, literally within 2 weeks, a group of neutrino physicists meeting in Seattle had an idea. Well, if you're going to close this mine, we need a deep hole in the ground. Why don't you just hand the keys over to us, and we'll convert it and make it turn into a national underground laboratory, because the Ray Davis experiment had about expended its usefulness. And they had a whole regimen of experiments that they wanted to do underground. So this was their idea. And this is the name that, if you've paid attention to any of these stories, you know DUSEL, the Deep Underground Science and Engineering Laboratory at Homestake. And this was the vision they came up with. Excuse me, a national underground laboratory with a campus, with a surface campus, with a 300-level campus, with a 4850-level campus, where Ray Davis's experiment was right over here, and a 7,400-foot level campus, which would be the deepest underground laboratory in the world. And then geologists were in on that at every level. And they also turned to biologists. And biologists want to go to the 8,000-foot level. And they want to have a lab module 8,000 feet underground, and then they want to drill a borehole, maybe about like this, another 8,000 feet down. So they want to go 16,000 feet underground. And why? Well, they're looking for life, extreme forms of life that can exist without oxygen, without sunlight, and very dark, very hot, high-pressure environments. And forms of this life have already been discovered in South African gold mines, more than 2 miles deep. So this would be the deepest anybody's ever looked for life. So this is the vision of Dussel. This is a kind of a more detailed, but a conceptual kind of look at what it would look like. This is the 300 level campus. This would be the Davis cavern. You can see it's tiny. You can see these are very large cavities, and these halls are huge. These halls are on the order of this room size, but longer. And then this would be the 7,400 level campus, and that would be a typical underground lab module. Imagine this is a horizontal view. This is the Ross shaft going up to the surface in the 8s. This is the Davis cavern. So you can see this is not exactly the scale, but it's partly the scale. It's kind of in the ballpark. And you can see these large mega detectors, which I'm going to talk about in a minute, would be just huge. And then these would be experimental halls also for smaller experiments, and then 6 winds going down to the 7,400, down to the 8,000, and there'd be another shaft here going down to the 7,400 level. So big plans. This is a cutaway of what we're calling the mega detectors would look like. This is the 4850 level, so you're looking horizontal. And then below this is about 65, 70 meters, and this is about 50 meters across. And they would have ramps built down to the bottom of them, and a big ramp down to access for construction. So it's a big vision. So what do you do with a detector that big? Well, one of the first uses for that big detector is being proposed by Fermilab outside Chicago, which is a national laboratory, a huge national laboratory, and they're currently operating the largest particle accelerator in the world. As soon as the one in Switzerland gets fired up and doesn't actually blow up like it did last time, that'll be the largest. But for now, Fermilab's the biggest. And currently, they shoot a beam of neutrinos to a much smaller underground laboratory in northern Minnesota called the Sudan Lab in an iron mine in Minnesota. What they want to do is they want to curve the beam around this way and aim it at us. So this beam of neutrinos would travel 900 miles, and it actually goes through the Earth because obviously the Earth is curved. So the shortest distance between Chicago and Lee is not on the surface of the Earth, it's through the Earth. So this would hit one of those mega detectors, and this concentrated beam of neutrinos, they still hardly hit anything. I mean, they're very benign. They would be nothing compared with the solar flux of neutrinos, but they'll know what kind they are and what energy they are, and they'll know where to look for them. So if they have a big enough detector, they think they can discover a lot of properties of the neutrinos, such as what is their mass and what kind of energy they carry. So that's it would be put at the 4850 level. That's kind of a not very to scale model of it. This is a similar detector. These are called water Cherenkov detectors, and they're filled with purified water. So this is one in Japan, and usually this would be filled with absolutely pure water. This is down for maintenance. And these guys here in a little rubber boat, 3 of them, and they're polishing these photo detectors. And what these thousands and thousands of very sensitive photo detectors do is they pick up that tiny flash of light of a neutrino. Yeah, it's quite a job. And actually, they had a big accident here about 7 or 8 years ago, and there was a jolt of some kind, and most of these photo multipliers shattered. It was unbelievable. They were down for like 2 years. But anyway, this is a detector that would contain 50,000 tons of purified water. The mega detector proposed at Homestay for the Fermilab experiment would hold 300,000 tons of water. So this is the Japanese experiment. This is the one at Homestay. So you can see this is kind of a big undertaking. That's to put it in perspective. Mount Rushmore would fit inside it pretty easily.